So in this video, we're going to talk about threads, multi-threading, cross-threading, if you will. Everything except specifically tasks, because they have a whole new thing that are built on top of threads and, the thread pool and things. So this is basically an introduction into the world of how threads work, how things in your code can run in parallel with each other, and how you then bring them back into sync, and all the little bits around that. So we're going to dive straight in. We're going to make a console app, a .NET Core console app, and start with the basics. So the first question, I guess, is what are threads? So threads are basically, you can think of them as sort of processing lanes for information that your application wants to process. So in this function main here, and we have a hello world, and we put a few of those in, and then at the end we have, say, a console.readLine. You can think of this as a set of instructions that happen one after the other, so in series with each other. So you come into main, then you hit line 8, then you hit line 9, you hit line 10, and so on. And this is the structure of your code. So if you were to put a breakpoint in here and run your code, then what you'll see is that you get into your code, you hit this line, and you press F10 to step over, and this is the next line, and then this is the next line, and it's a sequential order. It's obvious what happens, and then you get to the point in code where your program now is waiting for you to press enter, and then it goes to the next line. So that's almost, you can think of, and it is in this instance, a single thread. It's a single piece of information that happens line after line, and that's easy to understand in code. It's the flow, it's how things work. Everybody understands that who understands programming. That's kind of what's happening. Your code is expected that line 10 will run after line 9. Now, that's okay until you get to more advanced applications and you want to do things in parallel. So say you're downloading a picture from the website, or from a website rather, and you want to show in some UI, like a loading progress spinner, or at least the text loading, and you don't want to freeze up your entire application while it's downloading. So in order to do that, you need to spin up a new thread and to download the image on a new thread, say, and then once it's done, you come back and you update your UI. You could be doing a bunch of processing that you want to, say you're processing while you're working, but again, without hanging your application. So in a console application, it's pretty much straightforward. There's a main entry point and there's a single thread that runs here. And when this specific thread is done, the application closes. So if we were to remove console.readLine, this will simply run, output all the information, and close instantly without us seeing the application. So if we just put a breakpoint, because it's already ran and closed, it'll spin up, run, and there's the code. And then we press F5 because it's only stopped due to our breakpoint, and it closes. So this is the thread that's run and closed. So in order to, I guess, get familiar with things happening alongside this, we'll just basically create a thread and start showing you what happens. So we have the hello world, and that now runs, and when we run, it simply runs and waits for us to then press enter. So if we wanted to now do something while this is waiting, if you will, we can now start a new thread. So to do that, type new thread, control dot to open up the suggestions and include the system threading namespace. And then in here we do our function, or our action in this case, and now we're in a new thread. So here we obviously have to also start the thread at the end, so do a .start. This will now spin up a new thread, and in here this will basically start running, go to here, and when it gets here it finishes. So right now that's a blank thread that will do nothing, but in here we can at least do console.writeLine to show it's running. This is a new thread. And if we run that code, you'll see now that it says hello world, and then this is a new thread. So we've done things that look like it's the same as doing it one line after the other, but that's not what's gone on here. This is a completely separate thread. So what we can say is this is new thread 1. Copy and paste just for demo purposes here. You can do 1, 2, 3. And typically this is not really going to show you much because everything seems to happen in order due to just the way this is happening. But one thing you can do is say do a thread.sleep and put the thread to sleep for a second. And what you'll now find is that all three of them wait for a second at the same time. And if I could get this thing to keep opening in the right window, it's adamant it wants to open in the wrong window every single time. So let me just pause this application here until I press enter, just so I can show you that before it spins up. So if I press enter now, you get hello world, and then a second later all three fire. So what's happening is this thread's running, this thread's running, and this thread's running. All of them are running at the same time. So they all wait for 1 second between them, and then they all output their information. Whereas if you were to remove the threads, and you were just to run everything in a single thread, in a single series line, if you will, the behavior will be different. So this time, you'll get hello world, then the first one, the second one, the third one, because they're not running a new thread, they're all running the same thread. So this now follows a straight order. So what we've done here by introducing threads is that you can think of these as completely separate pieces of work that are being run all at the same time, if you will. So the CPU splits its workload up between all the threads in the application and assigns, micro chunks of time for these threads to be run. So they'll all kind of run in parallel. You can think of them all happening at the same point in time. And then that outputs the information. So in order to just simply demonstrate for one that a point I want to get across is that this thread, as you enter the application, runs and then ends, and will basically end as soon as it's finished. So if we went to there and run, and then we press enter, it'll say hello world, and then it will end. And the reason it also didn't end, by the way, as soon as it got to here, which it will have if we hit here and run the application, you can see we've got there, and it waits for these threads. And there's a reason for that, and that's because this thread, or new threads by default, are being created as foreground threads. So we're getting a little bit ahead of ourselves in terms of understanding what that means, if you will. So we'll backstep, and the first point I want to prove is that simply, if we were to delete the threads and we just remove that, as we demonstrated, this will now instantly close as soon as it's displayed that word. So as soon as this thread, this function here, gets to the end and is done, then it will basically close. So the way we can kind of show that is instead we'll create a task completion source, new task completion source, and we will now, instead of doing console.readline, we would do task.result, and we'll simply wait for the result. So now we'll hit this line, and effectively we'll never get to this line. So this will show, opens up, press enter, and we get to this line, and now we never exit. The program will never end because it's waiting for a task completion that never completes. So we've effectively halted our thread here, if you will, from ever completing. And now what we'll do, we'll start a new task, or rather a new thread, and inside here we will simply say thread.sleep. So let's wait for, say, 2 seconds, and then complete the awaited task completion source. So now what will happen is once this runs and we press enter, it'll wait for 2 seconds, and then it should have actually finished, which it hasn't. What's going on there? Oh, I haven't put the start. So we've obviously made the new thread. We need to actually start the thread. So let's try that again. So it starts up, hello world, and then 2 seconds later, it closes because this is finished sleeping. It sets the result here, and now this can continue. So the real demonstration here, and the point here, is that your console application in this case, and the same for all applications, with WPF applications, any other application, they have an entry point, which is typically a static void main, that comes in and simply runs the single thread that it's on until the thread ends, and then once that main thread's ended, the application closes. So that's how it typically works. There is an exception to that, and as you've seen, we can simply hold the application. If we delete that, so now the application should close straight away, as it normally does. But instead, we tell it to wait, say, for 10 seconds. Well, that's a second. No, it's not going to be obvious. If we tell it to wait for 10 seconds, now if we drag this in and press enter, we have hello world, and you can see, even though it should have finished, this thread that's running separately keeps the whole application alive. So 10 seconds later, this should then finally close. So the reason for that is that when we come into main and we hit here, so I'll show you the code. I've got down here the threads and the task windows. So if you don't see those, you click debug, windows, and then you've got threads down here and tasks, which we'll talk about near the end of the video. So in the thread video, you can see we've come in and this is the main thread, and there's the process ID and the managed ID of 0. So we have the thread, and as we step through, you can see that's the thread we're on. That's the grey thread that we're running on right now, with this arrow indicating that that's where we're breakpointed to here. So we're on this single thread, and we now wait for me to press enter, step over, and then at this point, we're going to create a new thread and start it, and then we'll hit inside the thread here. So if we press F10, you can see the thread's now been created, if you will, a new thread, and it should start. And we've hit the very next line. You can see there's no thread yet. We step over though, and you'll see now it's started this thread. This one's now finished, but we've now got a worker thread, and this has got an ID, and you can also see the main thread has now been destroyed. So even though the main thread that we entered in on has now since finished and completely gone, it's been destroyed, we've got a worker thread active, and because this thread is alive, the application won't end. And more importantly, because this thread is what's called a foreground thread, the application won't end. So now we've got this new thread, and you can see the arrow is now pointing to this thread, which means this one's, the thing that's active and running. And it's going to wait for those 10 seconds for that delay. And then when it finishes, it will obviously end the application, which I don't think we can hit any breakpoints at that point. It's basically the closure of the application. So 10 seconds later, this will simply kill the debug session. So if we wanted to show, and really the only important thing there with a foreground thread, which is created by default, is that foreground threads, the only difference between a foreground and a background thread is that foreground threads will keep the application alive. So if we were to change this thread to a background thread instead of the default, see if there's any overloads anywhere we can make use of. If not, we'll just simply change it here, is background equals true, and then we start it. So a bit of a weird looking way of editing the object on there. More typically, you'd do something like var thread equals new thread. You'd put your action inside here that does your work, and then you do thread dot is background equals true, and then thread dot start. So that's kind of what I'm doing here, but I'm doing all that in one line, so it just looks a bit strange on the syntax. But now it's a background thread. What you should notice is when we bring this in and we press enter, it says hello world and effectively dies straight away. And that's because this is now a background thread, which means it shouldn't keep the app alive. This simply gets run, and if the app terminates, it's simply killed. It's done an instant thread kill, if you will. So that's the difference between foreground and background. And that's kind of the explanation of how your application's working in terms of threads. It will come into this main thread. You'll have a thread, and that will be a foreground thread, and it's your only thread that exists. And then the application will simply run all foreground threads, which in typical circumstances is the only one. So as soon as this thread gets to the end, it would exit. Unless in the course of this thread, you make more threads that are foreground, and then it will wait for all of them to complete. Each thread that you have will run parallel to each other. So if we had 1,000 threads and all the threads were sleeping for 1 second, and then when they finished, we were done. And I won't do 1,000 because that's a bit extreme, but let's say enumerable dot range, let's do 10 threads, and we just cast them to a list, and then for each, and then in there. So all we're doing here is making effectively another way of enumerable.range just to do for var I equals 0, I is less than 10, I plus plus, ta-da, and then you'd put your stuff in there. But to me, this is a bit old school now for thread. I know this is not super efficient in terms of doing this, but efficiency isn't a concern in this one. Whereas this to me is a bit more readable. So in a range of 0 to 10, which in terms of the count, so from 0 to 9 in terms of what you'll get, but ultimately if you start with 0 and then put a number here, this is how many times you'll iterate. So we have a range of 10 that we do something for each item. So to me, this is more legible in code, but it's just a for each loop where, speed isn't of a concern. In this example, it definitely isn't. So it's just a quick and nice way of making a flexible for each loop where you don't really care about speed. So slightly off topic there, but that's all I'm doing here. So now we'll hit this 10 times, we'll run 10 threads, all of them will wait a second, and then the application should close. So what should happen is, once this is created all 10, the application should basically close. So in roughly 1 second after pressing enter, the application should close. And there is a bit of setup cost in terms of creating threads, so it won't quite be that quick, but we press enter, and then you can see it's gone in approximately 1 second. What it hasn't done is it certainly hasn't waited for 10 threads, waiting a second each. So you can see that these are all running. And if we put a breakpoint, you'll also see that once we hit enter, we'll have 1 thread running, 2 thread running, 3 thread running. You can see all the threads here being created. So you can see now we have all these threads. Some of them have since died since I run it because they're all obviously being run at the same time. But you can see by the ID, we have a bunch of threads running. So you can see them all running there. The other thing we can also do is say console.writeLine. And we can say thread, and we'll do thread.current thread. What is it? Sorry, not. Yeah, thread.current thread. Dot ID, manage thread ID. There we go. So thread ID. I know we just simply output the thread ID. It doesn't really matter. And we could also, yeah, that'll do for now. So if we run that, and then we are also not going to see, oh yeah, we'll see that for a second, which, so you can see that I've just grabbed hold. No, in fact, let's just chuck this at the end for the minute, just so that it stays open so you can see that output. You can see there the ID of the threads is a new ID per one. And in the course of doing this, it's already got the IDs aren't necessarily starting from 1 all the time, basically. But you can see that each of these threads is a different thread, and they've all run at the same time. And then we can also do, say, thread ended. So then when we look at this, you'll see the process of 10 of them starting and ending. So they're all running, and you can see the slightly out of sync number now to show that they are really running all on their own threads. So this is all running parallel to each other. So that's kind of the. Hopefully you'll understand that the basic principle is that when you start a new thread, it runs in parallel with every other thread that is in the application. And if you want to visualize that happening, then obviously just put a breakpoint in, show the thread window here, and then as you're going through and you're seeing threads being created, you can sort of watch them being created here. And you can also see by this arrow which thread you're currently in. So you know you're in thread number 5 here, then you're in 7, then you're in 6, then you're in 8. So you can sort of visualize what's happening to your threads here, and also the state and the line that they're on. And then you can jump between them to debug, to jump between any threads at any point in time. Now, one of the points I'd like to also make at this stage is you might be thinking, right, I've got a lot of tasks that need to be done. Or your code wants to do a lot of things. Your application's running, and maybe you're doing an application that's receiving a lot of data from a lot of places or does a lot of work. And your first thought now might be, let's spin up a load of threads, and on each thread we'll do different pieces of work. And then they'll all run in parallel and everything will work super quick. Say you're doing file encryption or reading chunks from a file and doing something with them. Maybe you'll think I'll split that up into 20 threads, and then 20 threads will be reading different parts of the file asynchronously. For whatever reason, you're thinking of using multiple threads. there's basically a warning. Don't create too many threads is the underlying sort of message. So things in code and things running in parallel are not always, and most of the time are not always quicker than simply having a single task that runs in a straight line, if you will. And that's because ultimately the CPU only has so many true cores that can actually run in true parallel. So on quad-core processors, for instance, you have 4 truly independent cores. And inside of there, you then have virtual cores that can go 64, 128. You can have a lot of virtual cores. But ultimately, for the most part, and how it was before, multi-core computing come out, a single core CPU only ever had one piece of information it could run for the whole system at any one point in time. And it simply worked on a super fast clock and allocated, nanoseconds of work between every single process on the whole machine. So at that point in time, threads and multitasking were in no way quicker than doing everything in sort of a single process, if you will. But ultimately, there are cases where multi-threading and doing things on separate in parallel processes gain speed, but it's not usually the case, and it rarely is the case. More of the time, when you want to use a thread or you want to do something in parallel, it's not for speed related purposes. It's more so, and the most common reason why people will probably watch this video, and the common reason why people want to know about threads and anything to do with threading, is the classic issue of when you have a UI. So you're running a Windows Forms application, you're running a WPF application, whatever you're running. And people that aren't aware of threads or how things work will say try and do some form of task or some form of computation or pull information from a database. And they'll just be doing it there and then, writing code. So you'll click a button and then they'll want to read something from a database. And what they'll find is that all of a sudden their entire UI is hung up and they're not sure why. And then they'll read up and they'll find out that it's because they're running worker processes, if you will, something that needs to do a task on the UI thread. And then that's where it kind of leads into this discussion. So don't really think of threads more along the lines of doing things quicker just because they happen in parallel. It's more to spread the load and to allow things to happen as you need them to happen in code. So like you download an image from the website or you download some data and you parse it, but while that's happening you want to be updating a spinner, or you want to go off and query a few other places, do some other things in code. So it's not always for speed. It's simply for having your code work without locking other, work up, if you will. Multiple things happening at once. So that's just kind of a little warning with threads. Don't go creating, like say, let's create 1,000 threads and run this. And you'll see that it will, in order to create 1,000 threads, when I press enter, you'll find that it is not exactly quick. That's pretty damn slow. That's very slow. So you can see it's creating, a thread probably taking 100 milliseconds to create. So this is not a quick thing to create a new thread. And we'll move on to tasks shortly, where tasks use what's called a thread pool. And the thread pool, instead of simply making a new thread, you can use thread pool .queue worker item. And if we change the call to this instead of a new thread, so we do queue new worker item, close that off, and we want to wait callback. So let's have a look at wait callback. Go in, and it's basically going to accept an object. So if we just pass an object we don't care about, that should be okay, and we don't start it. So now we use the thread pool to do the work for us, and we press enter. Oh, and go to there, and you can see now this is, and you can see the ID is being reused. So what's happening here, even though we've got 1,000 threads being created, it's reusing almost the same threads all the time, and it's not necessarily spinning up a load of new threads. We haven't got a continual increase. So the thread pool is a different thing again that we'll talk about. That'll queue up the work and reuse threads to try and cut down on some of that amount of work, if you will. But that's also got its own issues and a lot of things to talk about there as well. But a lot of that you don't need to really ever worry about the thread pool for, what this video is about. It's what we're trying to cover here is the simple understanding of threads in general. And we could talk for hours and hours and hours on cross-threading and thread pooling and recycling and and tasks, and there's all kinds of topics, but basically don't worry about them. Understand the core principles first and then learn what you need as the requirements pop up. So hopefully we understand, like I say, the principle of a thread, and in a header we know that this code is running independently and in parallel with the other things. So the next part I'd talk about then is going to be, where this builds up to, basically, is now you've got past a demo state and you want to do something real now. So in here, we want to, say, download an image, and then say that we've downloaded an image. So we want to simply say, we've downloaded an image, and once we're done, we want to continue. So we don't want this line here. So we do write line, and we can just say all done. So this is where we want our application to end. And in code, you naturally want to do your piece of work. And imagine this is a UI that I'm talking about here, that you don't want to block this thread because this is the UI thread. So in here, we want to download some picture. So we'll do var web client equals new HTTP client. And we'll do, say, web client dot get string. We don't care. It's not a string. It's going to be a, we can just do, first, we can just do my website, just call the home page. And you can see, if we do that, once we've finished this, we want to then allow this bit to continue. So if we were to say starting download, and then if we were to say done downloading, and this is all example code to kind of show you the flow of where things are going. So if we press enter, you can see it says hello world, all done, start downloading and done. Whereas that's not the order we wrote the code in. We got hello world, and then we want to start downloading, and when it's finished, say done, and then we're all done. So what we want here is, because this is, as you know, being run in its own thread, and this is the other, the first thread, the main thread. What if, at this point in code, we want to wait for this piece of work to be done above? So that's kind of where it will naturally evolve. As you start using threads in your real code, and you've got a bunch of work here, there's going to be some point in time on some thread or some call or some function you've got where, okay, this is now a function that says download an image, but you want to await that call. You want to say, right, once you've downloaded, I want to continue what I'm doing and process. But that awaiting, if you will, you don't want to lock anything. So we'll get on to tasks, which will be perfect for that. But at the minute, we want to stick with threads to kind of show that. So what we could do is say var thread equals new thread, and we don't start it, we just get the thread, and then we can do thread.start, and that will do exactly the same. It's just now that we have the access to the thread. So in order for us to effectively lock, and I mentioned you don't want to lock the thread, this is the point of why we'll move to tasks in a minute, but this is just proving the point. Say we don't want this line to continue until this piece of work is done. You can do thread.join. So by joining on to the thread piece of work that's happening, our current thread will simply await and not move until this piece of work is done. So this is just a really quick way of kind of showing it's a blocking call. So you can see it blocks the calling thread until the thread has done its work or been terminated, basically. So now by running this code, what you'll see is we'll have sort of a similar affair as if this was all run in one statement and we've locked it. So we press enter, hello world, starting done, and then all done. So it's this thread at this point has waited until this thread's done. Now this is not what you do, because all you've done here by joining is simply, it's effectively done this. You've removed that and you've locked again. So now we get the exact same response doing it this way, which is not what you want. But the point I'm trying to prove here is there'll be parts of time in code where you want to await and not continue. But what you don't want to do is block your actual thread. So if other work is happening on your thread, then you don't want it to lock by doing this, but in terms of a console application, there's only one time that you've only got one piece of work happening in order anyway, so it's hard to show in this context. So we will show it in a WPF application to show you the principles of doing that, and in a more real-world situation, which is basically this with a button. But I just wanted to show you a quick way to kind of, join onto that thread, if you will. So let's just first touch on tasks in the console application before we move to the WPF application, because once we go to WPF, I'm going to get some threads that appear for my stylus on my touchscreen and things like that, so that it'll murk the waters between me trying to show you the threads. So as you know, right now we have this thread, we create it, we start it, and then we read a line here. So we run this application, and I hit enter. Oh, a bit late now for hitting enter. Oh, there we go. So you can see we've got the single thread, and as we've shown, as you step over, you've created that thread, but it doesn't appear till you start. So once you start the thread, then you see the worker thread. So by directly creating a thread, you get a thread. Here you get an ID, and that's how it all works. So bear that in mind. And then now what we're going to do, because there's rarely a case where you want to use a thread. This is just being shown to give you the idea of how to directly create a thread. And majority of the time, though, what you want to use is simply a task. So there's differences. I'll show you the task, and then I'll kind of talk about why and when you'd potentially want to use a thread. But this is not the normal thing you'd do. So this thread will go. We'll cut this piece of info here, and we're back to here. So now, what you'll see me doing on all of my videos is using tasks. And all the task is, now I'm really oversimplifying it, so don't take this for exact science, if you will. This is not exactly what happens inside a task. It's a lot more complicated than I'll make out. But in order for you to understand what's happening, and all you really need to care about is, let's take a look at this example. Task.run. So a task now, in terms of what it is, and again, oversimplified just for explanation. You can see the task here, you can see it's an async result and it's disposable, and you got all this info. None of that you really have to bother about or care about. You'll learn it as you need it, so don't worry too much about that. But in terms of what a task is, when you do task.run and you've created a task and it's returning a task here, all this is doing, and again, I keep stating this in case you think it, I'm going to say all it does, but I'm talking simple terms here. It's not what the real code does, but you can think of it in this way. So all task.run is doing is queuing up a new threadpool.queue worker item, and then it's going to pass in your piece of work that you want to do. And all the threadpool.queue worker item is doing is there's one thread pool per process. So our entire application has one thread pool, and that can be assigned and created. It basically manages a bunch of threads. So creating a thread is an expensive process. So we do new thread. That is an expensive process to generate a new thread. So when we do new thread, we are directly creating a new thread. When we do threadpool.queue worker item, the thread pool keeps a bunch of threads open once they're created. And when the work on that thread is finished, it's then recycled and reused without having to be remade from scratch. So a thread pool is kind of a slightly more efficient way of creating threads rapidly, being created, deleted without the overhead. So the task.run, firstly, it doesn't create a brand new thread. It simply picks a thread from the thread pool, or rather the thread pool picks it a thread. So all that means to you is that if we were to do task.run 1,000 times over, and during the course of those 1,000 times, as we showed in the last example, things were waiting and finishing at different times, and then say there's a 50th thread comes along, but 20 of the other threads before it finished. So you're going to have a bunch of these 20 threads all floating ready to be reassigned. So the 50th thread will then pick up one of the old threads. So it's kind of like think of it as recycling. You're not always going to be guaranteed a new thread number. It's going to recycle the threads. So I can try and show you that, but before we go into that detail, let's at least just show you this running in terms of a task running instead of a thread. So we get into the application and we drag this up every single time. We press enter, and you can see we've got the main thread as normal. Then we have task.run, and then we have all done. So you can see now we've got to all done. We haven't yet got inside of this task, the first line, but you can see we've already got a worker thread. And then you can see the worker thread is the thread pool work queue. So this is now getting ready, and in the tasks window, you can actually see it's scheduled the task to run. So it's expecting to start. So the difference here is this thread is part of the inner workings of task.run. And then when we finally get inside of the task, and now this is our piece of work we want to run on a different thread, you can see we're inside this anonymous method here, which is on its own thread. And we also have this worker thread here. So we now have this task that's running on a thread, a task ID of 1, and it's linked to this worker thread here ultimately. This is running on this worker thread. So it looks slightly different in terms of keeping track of the threads. And you get this new view here of a task that's running, because tasks aren't always one-to-one mappings for your threads over here. So as you've made a task there, it's very similar to making a thread, and you can see it all happens very similar. But the key difference is, one, as I mentioned, it goes on the thread pool, not a direct creation. And the second important thing is a task is always created as a background thread, which means that this will not await for this to finish. So when we create this and run, if we were to remove the read line and press enter, even though this is downloading, this will just instantly exit. So we can prove that as well by, say, having putting an async into this task and awaiting task.delay 10 seconds. And if we were to run this application and press enter, it instantly closes. And that's because, as we showed again in the previous example with a plain old thread, it's a background thread, so it's not going to wait. So we're now creating them this way, and it's nicer and easier to do. So it doesn't look it too much right now. But in order to now have this wait, if you will, wait for this piece of work to be done, in a typical call, when everything becomes asynchronous, which is a bit outside of this video, you'd have async up here, and then you'd await like this, and you'd await that task to be completed. So now this call here won't happen until this call here is done. But the key important difference here is everything else that's on this thread that this, action has been awaited on will continue to run in the background, and everything else that uses that thread can continue to work. It doesn't block the call, and effectively doesn't block the UI if it's on a UI thread. It simply lets it carry on working and comes back. And there's a lot of code that goes on behind the scenes that allows that to happen. And like I say, I'll do a separate video specifically on tasks because there's a lot to explain and a lot if you want to dig deep into how it works. But this video is purely to get you familiar with things simply happening in parallel, and really just familiar with what threads are, how to at least look at them, how to create them, and how to start making use, I guess, of task.run. So I think that's enough in the console applications. Let me just copy this bit of code here, and we'll go ahead and make a new WPF application. So let's just close this solution. I'm just going to restart and try and get this thing to open up on the same window as well, so I'm going to keep dragging it onto the other window. But let's give it a go first. So new WPF app, go ahead and create that. And then we will just chuck in a button with a name so we can access it behind the scenes, my button. Content is hello. And then in order to visualize this, let me just first paste this in here, just so I've got it on my clipboard. And let me just copy and paste some code I've written, just a quick style, in order to, where are you? 1 second. There we go. I just made a quick style so that when we run this WPF app now, you'll be able to see the UI responding. So I can kind of show you a UI deadlock. So it keeps opening on that screen. Let's close that, reopen, and hopefully it remembers the window. No. Okay, let me just quickly kill this because it's going to drive me mad. Let me just restart this Visual Studio and see if it'll open on the right window. Okay, that didn't work. So for now, for some reason, I'm going to have to keep dragging this window up. So there's WPF application. You can see on hover we go yellow, and when we remove we go green. So you can kind of see that's the responsiveness of the UI. When we drag it around, this happens. So this is basically showing you the UI working, and these interactions and the UI that happens, the changing colors, is on one thread, and that is what happens in WPF. Everything on the what's called the UI thread, the main thread of the application, there's only one thing that can ever update the UI, so it can ever change the color or change the text or things like that. It's a single threaded thing, so that multiple things don't try and change the UI. Otherwise, it won't know what state to be in. So let me just add a quick click event to this just for demo, and let's show you a deadlock. So perfect example here now. If we were to do something on here, which here we go, this is exactly what somebody will probably do and has done 1,000 times over. We don't need the logs now, but what we are going to do is download my web page, if you will, the home page to my website, when we click the button. And the important thing is here, we are on, at this point, the UI thread. And we can prove that as well by doing, if we put that back in and do debug instead, debug.writeLine, on thread, and we'll simply print out what thread we're on, and that will be thread.current thread dot managed ID. And the HTTP client seems to have disappeared. So when we click this button now, just down here, if we go to the output and we clear that, we should see when we click the button, it tells us we're on thread 1. And more importantly, you won't see much now. I have to restart because it speeds up after the first time. The HTTP client will work quicker. But you can see when I'm hovering in and out, the color changes. So if I click and now hover in and out, see how it just froze there for a split second. So in order to kind of demonstrate that better, let me just change this to download a 20-something meg file. So we're going to change this URL to point to my download of some SolidWorks files. This is about 20 meg. So now this should take a lot longer to process. I'm on super fast internet, but still it should be a lot longer. So now the work we're going to do is going to take a while. So when I click this button and now hover in and out, that is not exactly doing what I wanted it to do. Oh, hang on, we've got get string async. Sorry, the thing we've got here is not awaiting. So what we're getting here is a task, not the result. So let me just first force the result. That's what the issue we're having. So this is getting, basically downloading the file. So now if we click here, you can see now the whole UI is hung. Nothing's happening. My mouse is not on there. Nothing's happening. But when the file finishes downloading, then all of a sudden it responds again. So this is a UI deadlock. This is when you're hanging the UI. So if I do that again and click, you can see I can't even drag the window. Nothing happens. And when it finishes, that window is just going to jump and respond. So you'll see that dump. There we go. So I'm sure you've seen that happen in your application before. Maybe not as long, but maybe say you've made a login page to your application and you press enter and then it goes and does kind of a web call, but it does it all synchronously. It does it like this. It simply goes off and tries to log you in. And in the meantime, while you're waiting for that, the entire application, the UI of the application is hung. And the reason for that is simple, as I mentioned. All of the UI on WPF and WinForms and most UIs has to be on a single thread. There's only one thread that can update the UI. And because when you click a button, that event comes in on that same thread. So you come in on thread 1, which is the main thread of the application. This work then happens on that thread. So then when you're hovering over the button, the thing that's responsible for changing the color tries to change the color, but the thread's busy doing this because this was done first. So now that thread is 100% consumed by working on this piece of information we've asked it to work on. So nothing else on that thread can be used. So that's kind of where you get the initial requirement to start doing multi-threading, if you will. And as we mentioned, you can do threads. So you can start a new thread and simply do the work as we've done. So you can do this and run. And then now this work will still happen, but what you'll find is on thread will give you a different ID. So if we clear down here to see and we click, you can see the UI still works. We need to start the thread. I always forget to start the thread. So you click here, clear this off, and you can see now on thread 4, but this is happily responding while it's downloading. It's not hanging the UI thread at all. So you can do the thread, or you can do, as I mentioned, instead of threads, we use tasks because they're more modern, they're easier, they run on the background by default. That's why we use them. So we just cut that into a task. It does exactly the same thing. So that task will automatically run. This time it'll queue up on a thread pool. Clear that so we can see easy. Click the button. You can see everything still works perfectly fine. Now, that's all good. You've solved one issue. You've now, say this was logging into the application. What's the first thing you do once you've logged into the application? You then go, right, I've logged in. Now I'm done here. So this is where you will be now, let's say, logged in. You'd then say change page, or you do something that makes the UI change. So you'd either display a message box, you'd update the UI. So in order to show that, we'll say, okay, then my button.content equals logged in. And before I run this, because I know this will crash now, press Control Alt and E and make sure common language runtime is checked so we get the exceptions caught. And if we run this application now, and again, this is what thousands and thousands of people do, and this is why they kind of start coming to multi-threading and what goes on. We click that button, everything's fine and responding, and then when we finally finish downloading that file, we should get this crashing. It can't still be downloading, surely. Maybe it's silently crashed. There we go, it's only just finished downloading. So now it's downloaded, we try and log in, and come on, slow. Wow, this is going really slow. There we go. And you get this exception. The calling thread cannot access this object because it's owned by a different thread, basically. So what this is trying to tell you, and this is, again, one of the most common exceptions, is we can't edit this content item because the thing that created this content was thread number 1. And if we go to threads, it's the main thread here. So this thread is the owner and the main thread of the application, and all UI is created on this thread and has to be in order to follow the STA standards. So we can't edit this content unless we are on thread 1. And because we are on, as the output shows, thread 4, we get this exception. And this is part of multi-threaded applications and being able to communicate with objects that are on and created on and live on different threads. So because the UI object, my button, was created on one thread, and we've jumped off onto another thread here and then tried to edit the contents, we can't do that. We first need to jump back to the thread that this object was on. So you might ask, well, how to do that? And in this specific situation, all of the UI objects in WPF, so my button, if we go to the type button, you'll see this is of type button base. The button base is a content control. The content control is a control. Control is a framework element, which is a UI element, which is a visual, which finally is a dependency object, which boils down to what's called a dispatcher object. So this big, long, huge chain of objects, all UI elements in WPF are part of this dispatcher object. I'll do another video on explaining that in detail, but the dispatcher is responsible for allowing other threads, if you will. It's responsible for a few things, but it's mainly responsible for allowing other threads to dispatch messages to the thread that this runs on. So effectively it allows us to jump back onto another thread, and we need to jump on the thread that this button was created on, and then we can do what we want. So what that means is we could do one thing. We could do mybutton.dispatcher, because that's part of the dispatcher object, and then .invoke. And then we could do a normal action as we do all actions. And then here, we could now mess with my button all we like, and this will now work. So we run this code and show that this works. And the reason this works is because, again, if we copy this into here to show what thread we're on, we'll say now on thread, and then we'll change content. So we click this button, we're on thread 4, we wait for the 20 odd meg download, and then once it's done, we should see down here, finally, I should have picked a smaller file. I'll probably change that to just a web page now we know that the responsiveness isn't an issue. When this is finally downloaded, internet must be getting slow. Come on. Internet's going really slow, actually. Something's wrong there. Okay, let me just kill that and make this quicker, because this is taking forever. This should now be super quick. So we will have this work done. We're on thread 4. And then now you can see now we're on thread 1. And it's also changed the text successfully this time to logged in 1. So what we've done there is we've jumped between threads. So if we click that button again, we'll get into here, then we'll get into here. So we click the button. You can see we start here. We have this code is now running on thread 4 here, showing by the arrow. So we run, and you can see then here, we've now jumped over to thread 1. We've managed to get back on the main thread. So that's kind of the purpose of the dispatcher. But all we're doing here is managing to get back onto the previous thread. So we could do that in many ways, but it kind of doesn't matter. So because the main window is also a UI object, as I mentioned, and we're in the main window, if we were to step into the main window and go to the window, which is then a content control, which we know then bubbles down to a control, framework, UI, visual, and then dependency, and then finally dispatcher. We already have a dispatcher because, like I say, every single UI element has a dispatcher object, which means it's got a dispatcher. That dispatcher will also be the same for every single UI because the whole application only has one UI thread. So what that means is we don't need to do my button. All we have to do is call the dispatcher of any UI element we have. So anywhere in the application, say you wanted your whole application to be able to jump onto the UI thread to do this. If you're already in a UI element here, you can do dispatcher.invoke, which is fine. But say you're not even in an object that's inheriting from the UI, you can instead do application.current, and then you can get dispatcher from there. And this dispatcher is the same as that one, which is the same as my button.dispatcher. So that's why you'll see in some WPF code, you'll see something like application.current.dispatcher.invoke, and then people doing that to effectively jump back onto the UI thread, if you will. And that's perfectly valid. That's how you can do it. There's no problems with that at all. So you just have to be aware of in applications for UI that this is when threading becomes a bit more relevant and a bit more obvious, that if you were to do things on the same thread as the UI thread, you have to be aware of what thread you're running on. Then you're going to lock the UI thread. And at the same time, once you've done with your work and you want to edit anything with the UI, you should also doubly make sure you are back on the UI thread. So there's two kind of phases to the work, which you'll see in the WPF Faceta Word application we're making, is that this is why you see a lot of task.runs, is to jump onto the actual, or rather make sure we're not running on the UI thread because we don't know who's calling us or where from. So it's kind of an assurance that we're off the UI thread. And then whenever we want to get back to UI, we'd call this application current dispatcher invoke to make sure we're back on the UI thread. The reason you won't see much of this happening in my application, though, is because we use view model binding, and by default, MVVM will jump us back onto the UI thread because of basically just how it works, without getting into too much detail. It listens out for notify property changed, and those callbacks happen on the UI thread, so this isn't required. But anyway, that's kind of another topic again. So the last thing I really want to touch on here. I don't want to go too far into tasks because, like I say, that's not the purpose of this video. It's purely the whole understanding threads and getting that concept in your head first before we move on to anything more complicated. But I do want to show that, again, this is not typically how the code is written for a few reasons. One is because this call is synchronous, so it's just a normal function, so it's going to run line by line. So it's going to run this line, then this, and then because that's in itself contained and runs, it goes to this line and this line. And you can see that happening if you add a breakpoint here and here and step through. You'll see what I'm talking about. So if I click the button, runs this line, then effectively this line here, where the yellow is, this top line, and the next line is down here because the parts inside here, this is now going to spin up afterwards on a new thread. So this is a synchronous call that happens line by line. So it goes here to here to here. And then asynchronously, it's going to jump back and come into here. And then this is now running independently. And because this is a task and how we want this to work, like I say, you typically wouldn't say that the content's logged in inside this function. You'd simply want to await this function. You want it to look cleaner than that. So instead, what you'd normally do is do await. And in order to await something, we need the calling function to have async before the type. And again, I don't want to go into too much detail, but you'd rarely ever and almost should never have async void because you'd expect it to return something, so to be an async task. But in this case, it doesn't matter. We're in a special situation where it's a event to, a click and nothing's actually awaiting this. We just want to be able to await inside. So let's first look at what this does to the threads, and then I'll explain more. So now we have an asynchronous click event. So now we click. You can see we're still on the main thread here, so nothing's changed. We're still on the UI thread. We step over, and in fact, I should have clicked down there first to make sure we see the exact same behavior. So we click here, we're on thread 1, and you can see now it's gone into here, and it's on a new thread, and that's because we've awaited. So now instead of going to here, continuing, it hasn't. It's now stopped. So now we haven't got to here because it's now awaiting this task. But importantly, the UI thread won't be locked, and we'll show you that afterwards in a minute. But now we won't hit this line, finish our function until this task is finished running. So now it's going to do the usual, and we're still on the same thread. And then when we've finished, it's going to get to here. It's going to download. But you can see here now we've jumped back onto the UI thread and done what we need to do. And now we continue here. So there's a slight important difference here, is that before we'd go into this function on thread 1, we'd call this line here on thread 1, and then we'd instantly be done because we weren't awaiting it. So that's it, we're out of it. The difference now is that it runs almost like in sync. You can think of it synchronously, and that's exactly what happens. So the code line goes here to here, to here, to here, to here, and then when that's done, it comes back out. So you can think of it now almost like when you're visibly reading the code, which is the whole point of tasks and awaiting. It now reads in this flow. It naturally happens. So if we were to then down here say my button dot, or rather, let's just output some debug. So we'll say debug dot write line 1. And we'll just chuck a few in so you can kind of see what's happening. And you can see the order at which it all happens. And you can see that all these should go in sequence now. So you have 1, 2, 3. The only thing that won't go in sequence actually is this, because this is jumping off to another thread and we're not awaiting that. But the invoke should be synchronous, which it is, so you'll still see that in order. 5, 6. So now if we run this and click the button, everything should still happen, but in terms of what happens here, it will look like it's happening in a synchronous fashion. So you've got 1, 2, 3, 4, 5, 6. But the important difference is, if we were to now output the thread.current thread dot managed ID, as well as the number we're on, you can visually see then the difference is that even though we're running what looks like synchronous, one after the other, we're bouncing back and forward between threads, but we're not having to think about that. So the task is handling that for us. So it kind of alleviates that work. So you can see 1 is on the UI thread, then 2 and 3 aren't on the UI thread, and then 4, when we've asked it to get back on, it is back on, and then 5 is off again, and then importantly, once it's finished awaiting, we're back on the UI thread again. So you can visually see here sort of the progression of it bouncing between threads. And like I say, the important thing is we don't have to worry about that. We are having that all done for us without us having to worry about that. So let's clean up this code one more step and get it to the point where this is how I would use a task. So say this was now a real bit of work and this is what I want to actually happen. We've now done async so we can await the task so it runs in order. And the point of that is so that after we've done and we're finished here, we can do something with the UI. So now instead of having to do application.current.dispatcher.invoke and all this stuff, we can now just cut all that out, await the work we want to do, and then finally update the button. And the reason this works, and as you've seen just, is because we come in on the UI thread, we tell it to await this task, which now spins off its own thread to do the work, so it's not blocking the UI. And now we're on, say, thread number 4 in here. But you've seen that after, once it's finished and come back off the task into here, we're back onto the UI thread. So now if we run this, you should see that we're on thread 4 there, if it continues to use the same numbering. So you're on thread 4, and when it's finished downloading, we're now on thread 1 here. And then importantly, it's updated the text. So if we do that once more, you'll kind of see that. So it says hello, we click it, and it's still responsive, and then when it's downloaded, it then says logged in. So this is exactly how I would actually use a task await and task.run. And like I say, I don't want to delve too far into tasks because I want to do a video purely on tasks. And the one other thing I would do is you wouldn't do .result. That's a rare occasion would you ever do .result on a task. You would await the task, just like we've awaited this one. So to do that, you'd obviously make the thing you're passing into the task.run async as well. And now you can await the result correctly. So you should never really get a task where you return a task and do .result. There's very, very, very few cases where you'd ever want to do that because that can deadlock for, again, reasons I don't want to go into. But this now looks like a real function. And this is exactly, like I say, how we do and would do things in UI to make them work correctly. And hopefully you can visualize and you can think of it that when you do a task.run, once you're in here, you're on a different thread, if you will. And when you come out of it, you're back onto the calling thread. So whatever thread you're on here, before you call the task, will be the thread that you're on here after the task. So that doesn't change. It's the bit in between that jumps itself off to a different thread. So the thread here is the same as the thread here. And the await simply makes it a nice, clean way of doing something here on a different thread, but simply coming back and continuing on the same thread. Now there is one exception to that, and at the end of a task.run or at the end of any task, you can say configure await, and that's configuring this await, and the only option is continue on captured context. So in sort of quick and simple terms, if we were to pass in false, what this means is, as we mentioned, we start here on a certain thread, which is the UI thread. When this task wants to await and start, effectively do this work and then come back onto the same thread, the configure await false says don't bother. So what it means is that once you enter this task, don't bother trying to remember where we were. Don't give a crap about this thread that we came in on. Just simply do this amount of work, and then when you're finished, spit me back out here on whatever thread suits. So that may or may not be the original calling thread. And there's rare occasions where you want to do that, and some people try to use this to avoid UI deadlocks mistakenly, which is if if you do something inside this task, which is awaiting the original thread that you're on inside here, you end up with a deadlock because this thread is waiting for this thread, but if this thread then waits for that thread, you end up with a deadlock. And by doing a continual wait, sometimes you try and avoid it, but that's not the purpose of that. This is not meant to be used that way. But in order to show that happening, if we just simply put that configure await in there to say, don't bother returning back on the original thread we came in on, when we click, you can see we're on thread 4 inside, and then you can see now we're on thread 11, this whole new thread. We're on a completely separate thread because we said we don't care effectively about returning on the original thread. And then obviously we now get the exception that we're not on the right thread for the UI, which is correct. So the issue with this, or not necessarily the issue, but you have to be super careful, is if you ever see this or ever use it, even though visibly looking at this, you'd say, we've come in on a UI thread, we should come out on a UI thread. That's not necessarily the case. So even though this code looks like it's written that wherever you are here means you're in the same thread here, that's not the case, because this changes the context in which all this code is running. So it's a pretty complicated thing to explain without a lot more detail about tasks and understanding. So I don't want to take that any further than that. But hopefully we've covered enough in this video that you get the point of threads in general, what they are, what it means, and it's simply another task that then runs in parallel with whatever other tasks that your application is running. I've shown you how to use them, create them. I explained the foreground and background threads, and then just briefly touched on tasks which ultimately rely on threads. So hopefully that's been a useful video. We'll continue this up next with another video where I talk about specifically tasks and go into the detail of the awaiting, the async, the running, the continue within, all now very specific on tasks. But until we've done this video, I can't really start with tasks because you need to understand the underlying mechanism, at least, in a short and simple way. So hopefully that's been enough information that's useful. And again, as always, if you want to support what I'm doing, I have a Patreon page that I'll put the link in the description. Any support for what I'm doing is greatly appreciated. Any questions on anything in this video, just simply ask. I do get back to all comments and questions. And as I say, hopefully this video was useful, and I'll see you in the next one.